So our next speaker can come on out. It's Jens Kober from TU Delft here in the Netherlands. He's a member of the Cognitive Robotics Department and the TU Delft Robotics Institute. And among some of his many awards are the 2022 Robotics Science and Systems Early Career Award and the 2018 IEEE RAS Early Career Award. Welcome.
Thanks a lot for the very kind introduction. Thanks a lot for having me here. I've been working with robots since 40 years. Okay, that's stretching it maybe a little bit. That's the kind of robots I was interested in back then. I was really busy working on my fundamental motor skills, grasping and these kind of things that enable me now to deal with these kind of situations. I believe we're still quite a few years away from robots being able to deal with these kind of things, so let's take a look at a slightly more structured environment, like in a supermarket. Doesn't look too bad. We should be able to solve that with good old-fashioned engineering. Almost, but not quite. So maybe a little bit of learning can save the day. We've already heard quite a few talks about robot learning, so I'm going to be very brief. You've heard a lot about imitation learning, the idea of learning from human demonstrations, or reinforcement learning, where the robot is learning by trial and error on its own. Jan already showed this video on the first day, combining imitation learning. That kind of gets us in the right ballpark with reinforcement learning. It takes some 50 trials or so until it gets the ball in the cup the first time, but then another few trials until it's very reliable. What we don't show you in this video, and which is also not in the paper, is how many times Katharina needed to practice until she could show a nice demonstration, and also not how many hours I spent on fine-tuning the reward function to avoid that it gets stuck in some kind of a local optimum. Now, if we look back again on how humans teach and learn, you'll notice that it's quite different. You won't have a teacher provide just some initial demonstrations or an initial reward function, and then the student or the robot is on its own. Rather, you're going to have intermittent interactions. You have a teacher, a parent, a caregiver, and so forth that are going to provide additional demonstrations, corrections, tips on what to practice, and so forth. You also have that for adults, and even when teaching other agents like this cute dog. So, I believe that introducing this idea is really going to be beneficial also for robot learning. So let's see how that looks like, again, for the ball in a cup example. Now we can start from zero, from scratch, but we additionally have a teacher in front of the robot providing corrections like move more to the left, move more to the right, move faster, move slower, to help the robot out. And then it takes only some 20 trials or so until it can catch the ball in the cup. If you look at the plot, that looks something like this. In red, we have pure reinforcement learning that takes at least 200 trials. In green, we have a method that uses only demonstrations and interactions with the robot to learn, which is quite a lot quicker. And then in blue, that's the proposed combination of reinforcement learning and interactions that you saw in the video. So you can see it's as fast as using the demonstrations only, but in the end, what we get is a significantly better final performance, because it really plays to the strengths and weaknesses of both the human and the robot. The robot is very good at fine-tuning things and doing things reproducibly, while the human teacher is very good at getting the robot in the right region. So let's move on to something slightly more practical. Unscrewing a light bulb. This is a pure imitation learning example, also from about 10 years ago, where we collected, I think, around 10 demonstrations with some variations in the environment, how many times you need to unscrew where the light bulb holder and the trash is, and so forth. And then you can learn to reproduce and to generalize this kind of a skill. But also there, we swipe some things under the rug. In particular, that the initial set of demonstrations we collected, they worked fine, but then when testing it, we figured out that we had forgotten some situation. So we went back, collected more demonstrations, retrained the approach, and then you might need to do a couple of iterations. Can we do better? So here is another approach some years later that we developed. Here, again, using imitation learning, we taught the robot on how to put a cucumber in the correct crate, and that works fine. But now we swapped the position of the two crates, and the robot no longer knows what to do. Actually, the robot in this case keeps track of what it knows and what it doesn't know. So what it's going to do is it's going to do as much as possible autonomously, and then when it doesn't know what to do, it's going to ask for help from the human teacher. So this little push here, which helps it to disambiguate the situation, and from then on, it can do the task autonomously. We also ran a user study on that. KT is the baseline using only demonstrations. Lyra is our interactive approach. And to keep it short, lower is better. So not only does this idea of interactive learning help the robot to learn more quickly, but also the human teachers largely prefer this way of interacting with the robot. Here's another example related to what I was talking about in the beginning. Here the goal is to do some restocking in a supermarket setting and get the milk carton in the shelf in less than 5 seconds. Again, starting with a kinesthetic demonstration, you can also use some other ways of getting the initial policy there. And then now at the bottom, you can see the game controller we used for the interactive corrections. We're correcting both the trajectory to make it more robust, but also correcting on where to speed up the movement. And then here's the final policy, and it nicely achieves to do the task very robustly in 5 seconds. The couple of examples I showed you so far were mainly single subsets of a task, and this is an example on how to actually make it work also for more complex tasks. This is from a competition we participated in 1.5 years ago approximately. Again, starting with a demonstration and then using a combination of imitation learning with some corrections, but then also in this case, some failure recovery behaviors using visual input for the really detailed control we need to do, and then coupling it with a higher level system that tells it in which sequence to execute these subskills. I won't have time to show you the whole thing. Here's just a little snippet. One of the more precise tasks of reinserting this electronics probe into the socket. And then also here, we really made good use of the human intelligence and intuition on how to use the environment to efficiently solve the tasks for wrapping the cable around these 2 hooks. So really using the constraints of the environment, and then in this case, sliding along the cable to very robustly do that. I really am interested in making it intuitive for human teachers. And there's quite a lot of different ways on how you can interact with the robot. You could provide action corrections, you could tell it to correct actions, you could do evaluative feedback. You can have either the robot active and asking questions or the human in the lead, or you can try to enable all of those. We managed to do that, and that looks something like this. Again, a more fun task. It works very well if you have a simulated teacher or if you are the first author of the paper. However, as you can imagine, having so many options is really overwhelming for the average user. So here, that's what it can do at the end. So those are a few of the devices we used for feedback in the examples I've been showing you. However, if you ask your grandparents, probably what they really want to do is yell, "Bad robot," at it. So that means one of the big open questions still is how to get all these very rich ways of interacting and teaching a robot in there. Could be language, but also subtle gestures and combinations thereof. Foundation models will definitely play a very important role in enabling that, but I still believe there's quite some ways to go to really couple these very vague and ambiguous corrections and feedback to different abstractions and really the physical embodiment and the detailed knowledge you need for interacting with the physical world. So, to sum up, I hope I could convince you that having interactions with the human in the loop is really a very promising way of doing that. And since I started working on it, it also has picked up a huge amount in the robot learning community. If you haven't watched this movie yet, Robot and Frank, I really highly recommend you do so. It very nicely illustrates how a non-robotics expert, a retired burglar here on the left, needs to be able to teach a robot on the right new skills in the way they prefer, with a very specific manner, even if that's totally out of the distribution that we use to train the robot. And one final thought, it's not only about robots learning from interactions with a human teacher, but it's also about us roboticists learning through interactions with all the stakeholders, like Carmen said this morning, but then also with scientists from other disciplines that really look at how it affects the humans. So cognitive science, behavioral science, psychology, philosophy, design, law, economics, and so forth. Thank you.
Totally agree. Robot and Frank is a fantastic movie. Any questions? There's one way in back. I'm giving our volunteers a stairs workout.
Thank you. Thank you for the great talk. I have the question about the generalization ability of the human interaction with the robot. For example, in different edge cases, will the human need to demonstrate a different position of the shelf to tell the robot to put in different shelf, or perform a stacking case with the milk box, for example? Thank you.
Excellent question. The things I showed you today were indeed very narrow learning cases. Based on the embodiment or the representation you use for the skills, it has some generalization built in, which I couldn't show you today. But then indeed the big question is how to get it back if you have a generalist model and to integrate in that. Maybe that's what you want, but in some other cases, maybe if it's related to trade secrets of a company, maybe it's actually not something you want.
Great, thank you very much.